Hi all, thank you very much for joining us. I'm Derek Shanks, the Market Manager for Geospatial Robotic Total Stations here at Trimble. Really excited to have Mikael Nordenfelt here with me today to bring to you this presentation on the Trimble SX12, which we were very excited to be able to bring to market this new instrument with the improving on the Trimble SX10 that we released a couple of years back, and now I will leave it to Mikael to take most of the hour to go through some of the technical deep dives behind it and really give you an insight into this incredible machine. There's, as I said, there'll be time for some questions at the end, but feel free to type them into the chat window as we go, and I'll facilitate that with Mikael. But I will leave it at that and pass it over to Mikael to take it from here.
Thank you, Derek. So my name is Mikael Nordenfelt. I'm a distinguished engineer within Trimble. I'm located in Stockholm, Sweden, where we develop and manufacture the SX12 instruments. I've been one of the engineering leads in both the project leading up to the SX10 and the SX12. So today, I'm going to cover a few of the technology areas that sets the SX12 apart from other instruments on the market. It's hard to talk about the SX instrument without mentioning the scanning piece, even though that was introduced already with the SX10. So we'll cover that. Then I will talk on the newly introduced laser pointer and what makes that different from anything else. And finally, some slides on the vision system that we've updated for the SX12. And as Derek said, we'll end off with some questions. So how do you combine real scanning into a total station? To answer that question, we need first to look at what is actually the difference between a total station and a scanner, and why is it difficult to combine it. So looking at a total station, it's an equipment that is built for accuracy. It's used to selectively capture discrete 3D points. So you can either use your rod and measure points to targets, or of course you can aim to VR targets and measure things. The key here is that you measure a few points. The actual measurement time is really small compared to the time it takes to select your points. So the selection of the points is made in the field. You're accurately aiming to something, and then you register the measurement to that point. And everything is reasonably slow. A 3D laser scanner, on the other hand, is all about speed. This time you have some large object or an area that you want to scan. You use a measurement beam that you move as quickly as you possibly can. The only information you give the instrument to the system in the field is the general direction to what you're trying to measure. And then you want the instrument to cover that area with points as quickly as possible. This means that the time spent in the field is reasonably short. On the other hand, you need to spend time in the office trying to make sense of the data you capture. So total station, accuracy, not very fast, whereas the 3D scanner is all about speed. So what does this mean for scanning with the total station? Well, we still need the highly accurate drives of the total station to be able to do the accurate aiming needed for the total station work. But if we just throw in the new distance meter that can measure really fast, we get into problems. Because if you can't move the measurement beam quickly enough, you end up measuring the same thing over and over again. It's not much use covering a doorknob at 100 meters with 1 million points if you can't cover a big area. So we need to find a way to move the measurement beam quickly. Early in the development of the SX10, we decided for a target to be able to cover a full dome with a 1 milliradian grid. That's 10 centimeter spacing at 100 meters. And we wanted to do that in less than 30 minutes. Otherwise, we felt that nobody would really use it. So can't we use the old trusty mag drive that we introduced with the S series a long while ago? It is really fast, as you can see in this animation. But the problem is that it's just not fast enough. And the inertia is too large, so we can't really go much faster. Any unbalance in the instrument means that we will alter the setup, and it's not really very practical. And even at this speed, that 1 milliradian grid spacing scan would take over 2 hours. So we had to do something differently. So what we came up with finally was to introduce a third axis of rotation. We keep the 2 servo drives for the total station work, the highly accurate mag drives, but we introduce a way to quickly move the measurement beam within the frame of the telescope. So more or less just shifting it side to side like this. So what's the use of this? Well, if we aim our instrument here, we are aiming to a wall or something like that. We start this beam deflection so that the beam moves side to side. We start the EDM so it runs at a high rate, and then we slowly sweep the vertical servo drives for the total station. What happens is something like this. So the points will be laid out side to side and create a band of points while we're going up. So instead of just measuring one column of points that is incredibly dense, we can spread this out. And with the SX10 and the SX12, we are measuring 16 columns of points at the same time. Now we just shift over here and do the same thing going down. So this gives us a means to more or less roll paint an area with points and very quickly spread out our measurements over a bigger area. So looking at a scene, you frame the scene, this is what I want to scan, and the instrument just starts covering the area with points in an up and down manner like this. And it becomes really efficient. So how do we implement this in the actual instrument? We looked at many different diffraction principles, but what we ended up with that worked best was a glass prism. So an octagonal prism that is rotating at a continuous rate. Right now we are using 10,000 RPM. The beauty of this, as you can see in the animation, the light is coming in from the left. We have a focused laser beam coming in. It will meet the surface where the angle of incidence continually change. And if you remember your school physics, you will get a refraction that changes the angle with the angle of incidence. As you can see, on the other end, the light beam will meet a new glass surface that is exactly parallel to the one that we entered through. And this will bend the light back in the same direction as before going into the prism. It's just that this creates a sideways movement of the beam. So it's not deflected in angular space, it's just moved sideways. So now we add a positive lens, and again, high school physics. Rays coming into a parallel to a lens is going to be bent towards the focal point of the lens. So this means that now we can create an angular deflection around the focal point of this lens. So what's the beauty of this? A couple of things. So in scanning mode here, it has the advantage of creating a sawtooth motion of the beam. As you saw in my deflection sketches on the previous slides, we need the beam to move from one side to the other and then just jump back like an old typewriter. Otherwise, you wouldn't get a uniform pattern. You can create that by moving a mirror or something like that, but it creates a lot of vibration and costs a lot of energy to keep that going. In this case, when the light beam coming in switches from one facet to the next, we get that jump instantaneously and without having to change anything in the control of the prism. The other beauty of this is that it gives us a gear ratio that we can control. So if we rotate the deflection prism 20 degrees, we can select the lens and other parts to get a lower deflection of the beam going out. Right now we have a gear ratio of about 20 times. So 20 degrees movement of this prism give about 1 degree deflection of the actual beam. This gives us an advantage in terms of accuracy. So we don't need an angle sensor on the deflection prism that is as accurate at the total station as the total station main angle sensors. It only needs to be 20 times less accurate, but still render the same accuracy on the outgoing beam. And of course, in survey mode, when we want to do total station work, we just park this prism in a static mode parallel to the lens so that the beam just passes straight through. Let's look at how we implemented this in the actual instrument. Here you can see the center unit of, this is an SX10 actually, but this piece is so similar, so we can use this. Let's pick away some covers. Here you can see the inner structure holding all the boards on the outside and all the optics on the inside. Up to the left, you can see the drive for the deflection prism, and you can hardly make out the deflection prism itself on top there. Let's remove some boards. Then we rotate this a little bit so that we're looking perpendicular to the plane of the optics, and then we just cut this through. Now you can see all the optical components inside the instrument. There's a lot. There's always almost 1 pound of glass in the telescope. On the top here, you can see the piece that is that houses the optics and the deflection for the EDM and the scanning piece. So here is where we transmit the beam. It goes through the deflection piece. That's a high vertical thing, the first element the light passes through. Then you have 2 lenses that makes out our deflection package, similar to what you saw in the sketch previously. And it goes out to the front lens. When the deflection prism moves or rotates, this beam is going to move sideways in and out of the screen. But to make this work, we also need the receiver. We need to receive the light coming back, of course. We need the receiver to move as well. So if the receiver doesn't look in the exact direction of where we transmitted the beam, it wouldn't work. You wouldn't see the light. Or you could expand the field of view of the receiver, but that means that you will catch a lot of ambient light that will destroy your measurement. So we actually need to deflect the receiver too. So the light coming back bounces through a different path of the optics and through the same deflection prism and into a receiving fiber. And the beauty of this is that we don't need dual control loops to control 2 deflections. Rotating this prism deflects both the outgoing light and the path for the incoming light. Okay, so we have a way of moving our instrument and a deflection. That means that we can spread out our measurements. Great. But to make this work, we also need an EDM that can do both jobs. We need it to be accurate enough to fulfill the needs for traditional surveying, but we also need it to be fast enough to make this into a real scanner. So we started off from the old trusted principle of time of flight that we use in the DR Plus in the S series. So the basic concept is easy. We send out the light pulse, we start the clock, we wait for it to bounce on something and get back. We stop the clock. And since the speed of light is known, we can calculate the distance. The difference this time, though, is that right now with the SX10 and SX12, we have a continuously moving measurement beam. So that means that every single laser shot that we send out needs to render a distance. With a survey total station EDM, you usually have time to adjust. We usually have some attenuation that we can move mechanically. We have time to do averaging. We have tons of time, even though for the user it's just a second, but in the electronics world, that's tons of time. In this case, one single laser shot needs to render a distance. So we picked up a few pieces of technology that was introduced in the Trimble TX8 and combined that with the knowledge of total station EDMs. So to achieve this single shot measurement, there's a couple of things that is needed. One thing, we need a really powerful laser source. Because if you look at something like a rock at 500 meters, only 1 in 1 billion photons that we transmit is actually received back to the instrument. So we need to send out a lot of photons to make this work. The other thing is that we need a direct sampling receiver. So in a scanning scenario, you have no clue of the distance. You don't know if the target is at 1 meter and you'll get the signal back almost instantaneously, or if the target is at 600 meters and there's a significant delay. So the receiver of the instrument needs to be active and look for the returning pulse at all times. And this is a challenge. Yeah, animation of the scattering and most of the photos not coming back. So looking at the laser source, we scanned the market for different alternatives, but couldn't find anything that met our needs. So we actually built our own. We started from all the components that is available from the telecom industry and picked the things that are generally used for signal amplification in long fiber cables, like the underwater cables on our large oceans. So looking at the laser to the right here, you can see that there is a seed laser, which is a weak but really good quality laser. It generates a nice short pulse with good properties. We feed that into a fiber. This fiber that is marked amplifier 1 is doped with erbium atoms. Into the same fiber, we also couple light from the first pump laser, which is just more or less ugly light. So pouring in lots of light of low quality that gets absorbed by these erbium atoms. So when the seed laser pulse comes along, it will pull out the energy from these atoms and gets amplified. And then we do a second stage of the same thing. So out at the end comes a pulse with the same nice properties as the seed laser, but amplified to a peak energy of over 1 kilowatt. Fibercom usually use the 1550 nanometer wavelength, and that's really because glass has a really low absorption for that. But for us, it's also an advantage because it doesn't penetrate the eye almost at all. So the laser class limits for this wavelength is more or less when the eye starts boiling, to exaggerate a little bit. But you can output much more energy in this wavelength than you could in visible or near infrared, for instance. We use a pulse repetition rate of 26 kilohertz, and the pulses is only 1 nanosecond long. So down at the bottom here, you can see the relation between the pulse repetition rate that gives us 38 microseconds between two pulses, and the pulse length, which is only 0.001 microsecond. It's hard to get a feeling for these times because both of them are really short. We don't usually work with these type of times. But to give you some perspective, if we would scale this up so that the pulse would become 1 second, the spacing between two pulses is actually 10 hours. So the pulses are really short, and there's much more of not sending light than it is actually sending light, which is needed for accuracy, but also a way of getting around the laser class problems. Another good thing with this fiber laser source is that it gives us fantastic beam properties. So looking at the fiber that can transmit gigabits of data, it has some properties, and one of those is that when the light leaves that fiber, it seems like it originates from a perfect point source. This means that we can keep this laser beam collimated very well, and it becomes the smallest spot available in any instrument on the market right now, which is great for both scanning and DR measurements. And of course, 1550, as I said, it doesn't penetrate the eye, so of course it's invisible. Moving on to the direct sampling receiver. You can look at the distance measurement, something like this. This guy hollering in the canyon, that's the transmitter. He screams something. He waits for the echo to come back. Our receiver is more or less just a small digital sound recorder. And what you get out from that is a sound file. It would look something like this. You can see the first wave shape there. That's the sound directly from the guy screaming. And we do the same thing in the distance meter. So we couple out a small fraction of the light transmitted that goes directly to the receiver so that we get a start event. And the second wave shape is the sound that has propagated to the other side of the canyon and coming back. The time between those, of course, and with the knowledge of the speed of sound, gives us a way to calculate the distance. Typical sampling for sound is 44 kilohertz, like the CDs. But now we want to do this with light. The speed of light is almost 1 million times faster than the speed of sound. So if you could bend the light following the surface of the Earth, it would propagate 7.5 full rotations around the Earth every second. Light is incredibly fast. So 44 kilohertz won't do. So we are using a 2 gigahertz sampler to record the level of light coming back to the instrument. So again, just to try to give you a perspective of how much information that actually is. So let's assume that every measurement that this sampler does, 2 billion of them every second, would correspond to 1 raindrop. So then the question appears, how big is a raindrop? And when I try to look that up, it turns out that there's a whole field of science that's trying to investigate and statistically measure how big raindrops are. But I picked a average value. So how much would 2 billion raindrops be? Is that sort of 1 barrel? No, it turns out that it's a little bit more than that. So it actually turns out that in this example, 2 billion raindrops would be 600 barrels. And that's the amount of data we receive every second. And again, with the relation between the 1 second and the 10 hours, the data that we actually want to capture and try to filter out, the event of the pulse coming back, only corresponds to about a bucket. So we have an electronic setup that gathers all this data every second, all the time, filters through it. So it's a more or less a average sized waterfall. I'm trying to filter out 1 bucket of water every second, and the right bucket. So all in all, and adding a lot of other technology magic that I won't go into the details of, we end up with a distance meter that can actually cover both jobs. The SX12 is the high-end total station with 1 millimeter accuracy on DDM and really low measurement spread. And at the same time, it can scan with 26.6 kilohertz at the range up to 600 meters. A good thing with designing a distance meter that can actually measure 26,000 measurements per second is that when you're doing surveying work, you have tons of data to average, which means that the measurement spread of this instrument is incredibly low. So moving on to the laser pointer. When we sat down to think about what to do with the SX10 bring it to the next level, one of the most requested features was, of course, the laser pointer. But the SX10 was the best total station we ever made, so we really wanted the laser pointer for the SX12 to be something special. So what would be a special laser pointer then? What is the ideal laser pointer? Of course, you need it to be visible. It should be visible in direct sunlight. You want it to be really small and round, so it's easy to accurately pinpoint something. And of course, you need it to be accurate. So it needs to be coaxial, and it must align with all the other measurement systems of the total station. So one way of making it visible, of course, is to have a really strong laser. More output power means that it's more light and it's easier to see. But again, we have these laser class limits, and we don't want to make dangerous instruments. So we really wanted to stick with either laser class 1, which is safe in all conditions, or laser class 2, which relies on the blinking reflex. So if you get this laser class 2 beam into your eye, you're supposed to feel it, that it is unpleasant, and you will blink or look away. So we don't want to go down the route of making a too powerful laser. Another way is to adapt to how the eye works. The eye is really much more sensitive for green light than it is for any other color. So in most cases in total stations, when you have a combined laser pointer and distance meter, you usually make it red, because red is the color where silicon sensors that you use for the receiver is much more sensitive for red than for green. So it's more convenient to make a red EDM. But in this case, we already have our scanning distance meter, so we don't really need to consider that. So making a green laser pointer makes it about 5 times more visible than a red one. And then, of course, if you want it to be visible, you want it to have a small spot size. So the eye doesn't really react to the total energy in your laser spot. It reacts to the amount of energy per area. So if you can focus the amount of energy you are allowed to send out due to the laser class to a smaller area, that will become more visible. So how do we make a small and round laser beam? Well, it turns out that most lasers, semiconductor lasers, definitely has pretty poor beam quality. Usually the transmitting area is not uniform. It's flat and wide, which means that the beam is going to be elliptical going out. And there's usually pretty far from a nice Gaussian beam, which is the ideal for a laser beam. The other thing we have to fight with is the diffraction. Diffraction is a phenomenon that acts on all wave motions, and light is a wave, if you want to treat it like that. And it says that if you're trying to squeeze light through a really small opening, it will start diverging. So if you look at the two examples of laser pointers to the right there, if we have a beam that is 3 millimeters wide going out and it's perfectly parallel at the exit of the front lens, it will start spreading, and at about 100 meters, it's about 40 millimeters wide. So this would mean a laser pointer designed like this will give you a really small spot the first couple of meters, but at longer ranges, it's not very good. On the other hand, if you let it be wider at the exit, like 10 millimeters, it will stay together much better. And at 100 meters, it's half the size of the one that had a smaller exit. Usually, you end up with a trade-off about 5 millimeters here for a traditional total station design, but I'll come back to how we do this in the SX12. Then we also have optical interference. This is also an effect of the diffraction, but if you obstruct the laser beam, if you have a non-symmetrical, non-circular aperture, the laser beam will start breaking up, and you see this weird diffraction patterns, as you can see in the image to the right. So we want to keep away from that. We want nice circular apertures to keep the laser spot round. So let's look at what we actually did in the SX12. I mentioned the advantage of fiber lasers when I talked about DDM. So we thought that, hey, let's use a fiber laser again. In this case, we didn't really do it the same way as with EDM. In the EDM, we actually create the laser. The laser is part of the fibers. The fibers are amplifying. In this case, what we did, more or less, is that we had a laser of semi-poor quality. You can see an animation up to the right. It sends out non-uniform light. Then we have a lens, and we try to focus it into a fiber. If we have a thin fiber that only accepts certain angles of incidence, we'll get a lot of insertion loss. But that's okay, because the light coming out on the other end is limited by the laser class. So if you just have a little stronger laser here and we sacrifice light in insertion loss, it turns out that the insertion loss is mainly the bad parts of the non-uniform part of the light. So what actually goes into the fiber is the nice part. And going through the fiber, it blends and merges a little bit more, and out on the other end comes nice uniform light. We selected a green, 520 nanometer. We decided to go for completely eye safe here, and that was also difficult laser class work combining it with the EDM at 1550. So we decided for laser class 1 and an output power of only 0.39 milliwatts. But as you can see down to the right, just the light coming out of this fiber is really nice and round. Another good thing here with the fiber setup is that it moves the heat source away from the rest of the optics. So the light coming out of the fiber needs to be coupled into the telescope optics at some point. At that point, you don't want to insert heat because that will affect the optics and the stability of the instrument. So with the fiber, we can have just a fiber end that doesn't generate any heat in the optics, and then we can place the laser itself somewhere else where it can be cooled to something that doesn't affect the stability. So let's look at, again, how we implement it. You recognize this sketch here from when I talked about the EDM. The EDM is housing on the top here. On the bottom, there's a sort of a shaft going down. That's where the telecamera is located. So we decided to couple the laser pointer in together with the telecamera. So the light goes this path out of the instrument. You can see the small 45-degree prism that bends the light just after the exit of the fiber. The light going through that goes down to the telecamera. So the telecamera is mounted on the flat light blue board on the bottom. This also explains something you will notice when you work with the SX12. You cannot see the telecamera image when the laser pointer is turned on. And as you can see, there's a simple explanation for that. Even if just a tiny fraction of the light gets scattered in the surfaces of the beam splitter prism down there and the lens is going out, too much light will come back to the camera and completely blind it. So when you have the laser pointer turned on, the telecamera will be disabled and you navigate the instrument using the two other cameras. Having it focused like this means that we can have a larger exit aperture. So it's actually 20 millimeters going out of the instrument, which means that the diffraction is much less than it would be. It also turns out, if you look at the physics, that green has less diffraction than red due to the shorter wavelength. So this means that we can create a really small measurement spot. So just how small does it become? So between 1.3 and 5 millimeters, we keep it at 3 millimeters. And I'm saying we keep it because we deliberately defocus a little bit, because at close range, you could focus it down to 1/10 of a millimeter, and it becomes incredibly unpleasant to look at if it's too small. So we found out that 3 millimeter felt like the ideal for a human eye to look at it and mark something. At 100 meters, it's grown to 6 millimeters, and after that, it keeps growing with about 3 millimeters per 50 meters. So how much more visible is this if you compare it to a typical total station? And when I say typical total station, it's a total station that uses a red laser for EDM and for laser pointer, including our own instruments. So first, looking at the power, we stayed with laser class 1, so it's actually much lower power than a typical total station that usually fills out the laser class 2 with 1 milliwatt. But looking at the spot area, at 100 meters, the spot of our SX12 is 6 × 6 millimeters, compared to about 40 × 40 millimeters from the typical total station. This is actually a 45 times smaller area. And then we have the factor of 5 from the green versus red. So all in all, this is a bit theoretical, but it gives us about 90 times more visible laser spot at 100 meters. That's a huge difference. And this gets exaggerated even more if you're trying to use the laser pointer to a ceiling or to the ground. The oblique angles in these setups will prolong the laser spot significantly. So with the SX10 or the SX12, you can still make out the center of this spot. So at this example, from 2 meters high to 10 meters, it becomes 15 millimeters long. It's fairly easy to say where the center is. Whereas for a typical solar station, it's already like 10, 12, 13 centimeters, and it becomes hard to see and hard to find the center of it. So how about accuracy? We need to speak a little about collimation of the laser beam. So the laser pointer, of course, is coaxial. It originates along the same axis, and it's adjusted to have the exact same direction in factory. So the laser pointer is coming out down here, and the EDM is coming out up here. But as you already know, all total station will have its own collimation error for all the different sensors. You are used to this with the crosshair of an S7, for instance, having one set of collimation error, and the tracker having another set of collimation error. We are working with so small angles that it's simply impossible to keep everything perfectly aligned. So things will move a little bit, and you need to take that into account. Looking at a traditional laser pointer, you usually have some type of adjustment for it. But because the laser spot is pretty big, you don't necessarily need to care too much about it. Now we make a really small spot, even at long distances, which means that we need to be more careful about the accuracy. So with the structure of the telescope, there is a small systematical movement between the laser pointer and the EDM. So if you cool the instrument down, you can see that the EDM bends a little bit in one direction, and the laser pointer bends a little bit in the other direction. This image, of course, is extremely exaggerated to show how this works. And then, of course, if you heat it up, it bends a little bit in the other direction. This movement is perfectly systematical, and it stays the same. So as long as the instrument can measure its temperature, which it can calculate how much beams have moved in relation to each other. So that means that the software and the application in the Trimble Access can manage this for you and make it accurate, even in the extreme temperatures when this error can become a little bit noticeable. So when you are doing topo measurements, you should do that in standard mode, because in that mode, the system will help you to make the measurement accurate. So in standard mode, the laser pointer spot is steady, so it just shines with a steady light. And now in this mode, the laser pointer is the aiming reference. So the angles you see presented is referenced to the laser pointer. The EDM in extreme temperatures can be a little bit to the side of the laser pointer. Usually the laser pointer is within the spot of the EDM, but it can be on the outskirts of it. At this point, the distance, the EDM is running in the background, but those measurements are only used to focus the laser pointer. So when you press measure, what will happen is that the instrument turns off the laser pointer. It re-aims the instrument to where the laser pointer was, so that the EDM ends up on top of where the laser pointer just was. It registers the measurement, and then it moves back and turns the laser pointer back on. So as I said, the instrument is calibrated. It knows exactly the relation between these two laser beams at a given temperature, and it will correct this for you. So accurate topo measurements in DR should be done in standard mode. What about stakeout? So in stakeout, it's ideal to use tracking mode. You want to continuously have the updated position of where you're aiming. But given that we have this slight misalignment, the laser pointer is now blinking. The blinking pattern is actually not like this. It's a dual blink and then a pulse, a dual blink. But I could get PowerPoint to do that for me, so bear with me. So right now, in this mode, the blinking of the laser pointer indicates that it's not the aiming reference. So the aiming reference is where the EDM is. So now you can iterate until you're happy with the deltas. So you find the point that you want to stake out. And now in Trimble Access, there's a new button on the bottom right that says Mark Point. When you press that, what happens is more or less that the instrument switched to standard mode for a while. So it re-aims so that the laser pointer ends up on where the EDM just was. The laser pointer goes steady to show you that now the laser pointer is accurate. So you can mark your point, and then you press accept, and the system goes back into tracking, and you can keep staking out the next point. So how accurate does this system become with all these compensations in place? So we have the really small, nice measurement spot. But thanks to the firmware and the calibration, we also have the means to manage temperature drifts over the full range of operation. And the accuracy that we've been able to measure is, in worst case, I would say, mostly it's much better, at something like 2.5 millimeters at 50 meters range. So it's really pretty accurate. But make sure to do accurate topo measurement in standard mode and use tracking for stakeout. A few tips and tricks. There are a few settings related to the laser pointer. You can find them under, if you hold long tap on the laser. One is the laser power mode. In dark environments, even the 0.4 milliwatts that we have is a lot. So it's going to feel really bright. So you can set it down to a low light mode where, I don't remember the figure, but I think we take out about 90% of the light. It's still very visible in dark conditions. And then, of course, you have the standard. And then we also have a mode called extended range flashing. And this is what you use outdoors when it's hard to spot the laser pointer. So what it does is that it's a mode that sort of tricks the laser class regulation. The laser class regulation have one limit for the average power over time, but it also has a limit for the maximum peak power. So now we condense our average power into pulses. So it flashes fairly slowly, but the peak power that we can have in those flashes is about 2 times higher than the standard mode. And also the flickering of it blinking makes it easier for the eye to pick it up in the bright environment. It's much easier to see something changing than to see a static point. So that's something for really bright conditions. There's also a setting to have the laser pointer blink a couple of times to acknowledge a measurement. We've also introduced a new form of aiming. But the laser pointer, you know that the SX12 doesn't have any control knobs like the old S series. So we needed a new intuitive way to aim the laser pointer. We call it the dynamic joystick, and it's a way of mimicking the way you're used to navigating things on the touchscreen, like when you're moving around in Google Maps. So this is how it works. You go into the joystick settings, or the mode, press dynamic. Now you can both make big movements by just using these sliders on the right and the bottom. When you release it, it stops. But you can also tap and drag on the screen, and the laser pointer simply just follows your movement. So you can more or less draw something on the wall with the laser pointer and just slowly slide it into the center. There's a fast and a slow move that makes it really easy to pull it into the exact spot where you want to aim. Try this out, it's really convenient. So moving on to the vision system. In the SX12, we have a fully integrated and calibrated camera system. We have upgraded it from the SX10 with a new image sensor and a completely new image processing pipeline. And in an SX12, the cameras is used for everything. It's for instrument operation and aiming, and for documentation, and of course for measurements, even in post-processing. We have 4 cameras. We have the telecamera, which has the same duty as the telescope of a traditional total station, but we also have 2 additional cameras with different field of views. An overview camera with about 60-degree field of view, and a primary with 12-degree field of view. They're bundled together like you are used to see in modern cell phones with several cameras. So you don't really need to consider which camera is active. You just zoom in and out, and the instrument just switches between the different cameras. So in the video stream, you have actually 112 times zoom from level 1 to level 6. And level 6 is from the telecamera actual pixels on the sensor, where level 7 and 8 is just digital zoom in that image to just expand everything to make it easier to aim accurately. We have a piece of software active all the time that calculates the position of the crosshair. So this block continuously calculates where the crosshair is supposed to be, transmits that to the control unit so that Trimble Axis can overlay the crosshair in the correct position. It uses information of course, which camera is active and the calibration data for that. It uses the distance. You can also see in this video here that it's used for continuously focusing. It uses sensor data, predominantly the temperature of the instrument. And of course, all the calibration data from the factory about the different cameras. The crosshair that is overlaid in Trimble Axis has 2 different appearances. The one you see here is with a small cross in the center. That cross tells you that this calculation has succeeded. This means that the crosshair is overlaid exactly where the EDM is located. If the small cross in the center gets removed, that means that we don't have a distance usually. So if you, for instance, if you're aiming to the sky, that will be removed. And in that case, we cannot correct the crosshair position. So it's more like a guideline. As you saw from the earlier image with the different cameras, the overview camera and the primary camera is non-coaxial. The telecamera is coaxial like a traditional telescope, so that's not a problem. But for the other one, there is a parallax. So the closer you get to the instrument, you have to move the crosshair more and more to the side of the camera. And this is managed by this crosshair calculation, and you don't really need to consider. As soon as you see the small cross in the center, the instrument and the system has done its work, and the crosshair is painted exactly where the EDM is located on the surface. And again, the EDM is always on in the background, even in standard mode, to make sure that we have all the information needed for the crosshair overlay. All the lenses in the system is high quality glass optics. It's optimized for temperature stability and for stability over time. And any remaining temperature influences are calibrated. So this is an image of our factory in Danderyd, one of the test lines. We have 8 of those. You can see close to the instrument, there's tons of different collimators, which is more or less telescopes that projects a target to infinity that is used for measuring different things. You can see the checkerboard targets that are used for cameras at short range. And further out there, it's a bit fuzzy, but there's tons of scan targets and different other targets. So looking at the cameras, we calibrate a couple of things. We calibrate the lens distortion for each of the cameras, which is essentially the relation between the lenses and the sensor. So for the sensor coordinate frame, exactly what direction does each pixel look out to the instrument? Then we calibrate the lens geometry, which is essentially where is the camera placed in the telescope frame and the instrument frame. We calibrate the autofocus so that there's a good relation between the distance meter and the focus. And all of this is temperature compensated. So we measure all of these things at -20 degrees, at 20 degrees, and at +50 degrees, which means that we have compensation tables for the full range of operation. So looking a little bit at how to use the Trimble Vision. Of course, we have the plummet camera, which is just a camera looking down to a shaft through the base unit, the axis system. It gives you it's really convenient to use, and it has an accuracy of about, or accuracy is about 0.5 millimeter, and 1 pixel is about 0.2 millimeters on the ground. Much more convenient than looking into something on the instrument. Then, of course, all the normal operation will be done with the cameras, which is convenient. It's ergonomic. You don't have to stand there hanging on the instrument. It works for every setup, even if you have to put up the instrument really high or really low, or at the ledge or something, or in a ditch, wherever. The instrument doesn't care, the cameras just work. And especially for multiple DR shots, it's really convenient to just zoom in and out. And also for regaining lock, it's easy to zoom out, see yourself, tap on yourself, and zoom in, and it locks on again. And it's actually more accurate than the traditional way of working, especially since you really don't want to touch the highly sensitive setup of the instrument. You have a setup of the instrument where you're trying to measure millimeters at 100 meters range. You don't want someone touching the instrument and risking of kicking one of the tripod legs. So getting the user away from the instrument is actually one of the best things we can do for accuracy. The cameras is also a really good way to validate while you're in autolock that you're on the right target. So having the video stream rolling while you're in autolock is just a convenient way to trust the instrument. So aiming with a telecamera. Here's an image at the part of a power line, 200 meters almost. We're now in zoom level 6, so that's the highest zoom level where 1 pixel on the screen is 1 pixel on the cameras. We blow this up a little bit. The red circle represents the size of the laser spot at this range. So it's really easy to pinpoint that and get a good measurement to that. And in this zoom level, 1 pixel is about 0.69 millimeters at 50 meters. So it is really accurate. We've done a couple of different user tests where we had operators, both skilled and untrained, doing repeated aims with both the SX12 camera system and the S7 telescope. And we found out that the aiming accuracy was about the same. For the unskilled workers, it was actually a little bit better for the SX12. But on the other hand, the SX12 isn't really a tool for an untrained user. So we say that it's about the same. And then, of course, we have the documentation piece. So this is our office building in Danderyd. And this is actually a panoramic image captured from the instrument where it's just overlaid in Trimble Access. There has been no morphing or stretching of these images based on patterns. So it's just using the calibration from the camera. And they blend together almost perfectly. You can see a little bit in the sky where the clouds have moved between the exposure, and that's a little bit out of our control. And this is so the lines differs the images. So capturing a panorama for each station with the overview camera is pretty quick, and it's an incredibly good way to sanity check your measurements. You can overlay all your measurements in this image. And since we have calibration, they will end up on the right spot. And now you have a chance of noticing if something has gone wrong with your work or if you have forgot something. It's also a great way of creating context for the post-processing work in Office. And of course, since the images is calibrated, we know the exact direction for each pixel. You can combine the scan data and the panoramic images so that you can colorize your point cloud, which gives even better context. And it's also a way for you to extract data points that you might have forgot to measure once you're in the office. There are other webinars on what you can do with scan data from the SX12, but I'm not going into detail here. And then we also added a new feature for the SX12, which is telecamera panoramas. So here you can see a scene of a parking lot close to our office. Now we've done a telepanorama of this area, and this is just part of one of the images with the amount of detail you can capture. So covering the full field of view of the overview camera with telecamera images would take about 500 pictures. And that would be about 3,000 megapixels of data. So it might not be for that big areas, but it's a way of capturing immensely detailed pictures of areas, which is a good addition. So comparing the SX12 to the SX10 camera system, we have moved to a better, more high resolution camera sensor, which gives you better resolution in all the cameras. We've also built a completely new image processing pipeline that improves the color rendition. It has a better management of contrast. The exposure algorithm is more robust. And we also add a temporal noise filter using several images in a row to suppress noise in low light areas. And that's especially good for low light aiming. So overall, it's a significant improvement of the camera system. So the key takeaways here is we managed to put in real 3D scanning while keeping the highest accuracy on the total station. We have added the laser pointer so that we can have a really vivid, eye-safe, and really accurate laser pointer in the same instrument. And the cameras for improved operation and capabilities of documentation, and also the improved accuracy of not having an operator touching the instrument. So it's a great tool for every job, everywhere, every day. And that was the last slide. So do we have any questions?
Thank you for that, Mikael. Yeah, there's been a couple come through, but yeah, please, if you have any questions, put them into the question box on the panel and as part of the webinar. And for the ones that we don't get to, with the few minutes we have left, we'll get back to you after this webinar as well. Just a couple of other things. The recording will be available and will be sent to you since you have registered, but also be available on our SX12 webpage. So geospatial.trimble.com/SX12 is where you'll be able to find it and get access to it as well. So a couple of questions that have come through. One of them was, is the laser pointer standard for SX12 instruments? So I'll grab this one, and yes, it is. So we have one instrument configuration, which is the 1 arc second, and includes the laser pointer. So all SX12s come with the laser pointer hardware. Another one for you, Mikael, is how's the different light deflected to where it needs to go inside the telescope? You know, some of those diagrams showed a lot of light going to different places. How do you keep it all separate and send it where it needs to go? Yeah,
so we're using different optical coatings. Some of the easy ones is the different sensors using different wavelength or different color of the lights. So we can just use coatings that transmit one form of light and reflects another. And that's how we separate EDM from the visual channel, for instance. It's a little bit more tricky down in the telecamera channel, where the laser pointer is green, and we also need green light passing through into the telecamera. So what we've done there is, again, sacrificing light. So the largest portion of the light coming into that channel will get transmitted down to the telecamera because we need light for the camera. Whereas actually the major part of the light coming out of the fiber is just wasted and not reflected in that corner. But again, the laser class regulates what we send out of the instrument. So we can just have a more powerful laser and sacrifice light going into the fiber, and then again, sacrificing light, coupling it into the optical channel, and still keep the right level coming out.
Great. And next one here, you talked a bit about the autofocus of the laser pointer and being able to, if we wanted to, we could make it a lot smaller or adjust the focus. And the question was, is there a manual focus option for the laser pointer? So I can grab this one as well. But yeah, in Trimble Access, there is you can switch into a manual focus option and step through the different focus levels. And so if you do want, especially at short range, you can. If you want to go and make a tiny dot, you can do that with the manual focus option in configuration.
What you'll find out doing that is that lasers are coherent, which means that the light sort of interferes with each other. And when you make it that small, there's a laser effect called speckle, where a large disk of laser light will sort of get speckled. So it's spots that is bright and spots that is dark. And when you go that small, the laser spot becomes difficult for the eye to see. So I don't think you'll be very much more accurate, but yes, you can do it.
And another question here around the full dome scans in terms of timing, how long will it take? So it's just under 12 minutes to do a full 360-degree scan. But if we have a very simple horizontal band method in Trimble Access, where if you tap above the horizon, then it will capture everything from that point downwards, and that can say you're outside and don't need to capture a whole lot of sky, you can very simply drop that scan time quickly down to around a 7-8 minute for a full 360 degrees. So it does depend a wee bit, but yeah, in that range of 7 to 12 minutes for the scan, and then a extra couple of minutes for the pictures, depending on which camera level you want to choose. Another question here, where are the SX12s manufactured?
It's manufactured in our factory in Danderyd, Sweden, just outside of Stockholm. So one set of stairs down from the R&D department, which is extremely convenient. And I think it's a part of the fact that we can keep such high quality and do these things. It's incredibly difficult to manufacture this instrument, and I don't think we will be able to pull it off if we manufactured it in some remote country. And
yeah, time for a couple more. If you do have any others, please type them through. The question is, can I upgrade my SX10 to get the additional laser pointer? And the answer to that one is no. The SX12 is a brand new instrument. The laser pointer's there. It's not something that we can service upgrade on SX10s. Another question: what office software do you use with the SX12? So we have a couple of options there. There's Trimble Business Center and Trimble RealWorks. Trimble RealWorks is a very powerful scanning software for a lot of the scanning specific type modules. There's a tank inspection module that can be used there, but TBC, Trimble Business Center, is the main office software where you can bring in the survey data, the scan data, all coming out of the SX12, and for post-processing there, and end deliverables, and a lot of tools for manipulating the scan data there, and then you can also export out of there in standard formats if you need to. Okay, well, I think we will leave that there. But yeah, thank you very much, Mikael. And as I said, the recording will be made available, and look forward to talking to you all soon. Thank you very much.